Okay, so let's look at soil methane as well before we move on to how much carbon we can actually sequester and how long can we keep it there. Soil methane sinks. Some microorganisms like methanotrophs in soils have the ability to consume limited amounts of methane, helping to remove some of this powerful greenhouse gas from the atmosphere. But this methane sink is very small compared to methane emissions coming from agriculture as a whole. So while methane sinks can be improved, it's very important to note that landscapes only have very limited ability to absorb and consume methane, even as agricultural sources, especially livestock and manures, are leading methane emitters to the atmosphere. In fact, global grassland soils can only capture up to about 15% of the emissions coming from grazing ruminants each year. So it's not a soil is not a significant sink of methane. Head of cattle, but there are some studies going on engineering soil microbiome that I have a podcast on. Maybe someday we will go after methanotrophs as a much larger fraction of the soils without having any other negative consequences. So here is a herd of cattle grazing on Brown's Ranch in North Dakota and Silvo pasture, which is obviously mixing nicely trees and grazing land for cattle. So it's a more sustainable way of doing cattle production without degrading soil carbon or making sure that we continue to enhance soil carbon sinks. Finally, soil inorganic carbon. Much of the focus on agricultural carbon sequestration has been on soil organic carbon, but soil inorganic carbon is also significant. Soil inorganic carbon persists in soils and in groundwater for much longer than organic carbon. That's important to remember. And the world's dry lands, which are disproportionately low in organic carbon, store some 95% of the world's soil inorganic carbon. Researchers are beginning to explore how sustainable land management practices in dry land help to increase soil inorganic carbon levels. Practices to increase soil SIC include managed grazing, agroforestry, and applying rock powders for enhancing soil inorganic carbon through weathering, I suppose. Dryland restoration in Mali. So this is about soil inorganic. So this is dry land which has soil inorganic carbon, but you are also adding soil organic carbon, I suppose. Finally, how much carbon can we sequester and for how long? There is increasing interest in sequestering carbon on agricultural lands, but with that interest has come some extraordinary claims and a great deal of confusion. A handful of individuals and organizations have claimed that agricultural practices could, all by themselves, completely stop climate change. That's a big claim. That's not true, as we demonstrate below, but there are still many questions about how much of a role agricultural carbon sequestration can play in addressing climate change. To understand how much carbon might realistically be sequestered on agricultural lands, we can start with the basics. First, how much land can be used to actually do carbon sequestration by engineering, such as these efforts? Secondly, how much can each hectare of land sequester in reality? Can you keep on increasing the amount? So here are some numbers. Our area available for agricultural carbon sequestration, millions of hectares available in ag biosequestration AGB that we mentioned before. Note that estimate from Griscom is lower than the other two, as they use more conservative figures for the area of grassland that is amenable to carbon sequestration through improved grazing and pasture management. So you have grazing land and cropland, so there are multiple estimates. Ratan Lal, the world's well-known soil carbon expert, estimates 4,500 million hectares. Drawdown estimates about the same, with a little bit less, but they are more here on grazing land and less on cropland. Overall a little bit less. Griscom is much lower compared to the other two estimates because of these reasons here on underestimation of grasslands that are available. Second figure here, lifetime impact of agricultural biocarbon sequestration, or whatever this is called. Ag biosequestration. Lifetime impact and soil organic carbon. So LAL has low and high estimates. Drawdown has multiple scenarios. Zoomer cropland only in low and high estimates. Chapman has low and high estimates. So these are all gigaton CO2 equivalent, but you can see the high estimate of Ratanlal is very high, and Zoomer's high estimate is also significantly high. Here this is again ag biosequestration in gigaton CO2 and soil organic carbon. So here both of them higher. This one only does soil organic carbon. Here lifetime potential grazing land gigaton CO2 equivalent. So again, this is for croplands, this is for grazing land. So Ratanlal again provides a huge estimate for both, and in his high, but his low is even higher than some of these estimates. Ag biosequestration, Chapman low and high are very low compared to LAL. Drawdown is somewhere in the middle, but the uncertainty is obvious. These tend to be very small scale, and you're estimating at a global scale, and you're making all sorts of assumptions with very little ground validation at as many locations as you would want. What are the conclusions? We must change agriculture to help address climate change. The world's food system, agricultural practices, and land use are a significant contributor to climate change, together emitting roughly a quarter of our current greenhouse gas emissions. Most of these emissions come from land use, especially deforestation, methane emissions mostly from cattle, and nitrous oxide emissions primarily from fertilizer overuse and manure. To help address climate change, we must reduce these emissions first and foremost. In this primer, we have outlined, some say primer, some say primer. Primer is like a paint, a coating before the paint. So primer may be better, I don't know. So we have outlined here a wide variety of ways to reduce agricultural emissions, which together present highly actionable steps towards addressing this part of the climate change problem. Here are some emissions reductions versus biosequestration impacts. Again, I'm being very brief, so you can go back and read up more. Emissions reductions from biosequestration in soils and biosequestration in above ground biomass. Timeline of impact can be immediate for emissions reductions, and for soils biosequestration can be delayed, may take several years to begin, and here delayed means take several years to begin again, even for the above ground biomass. Lifetime of impact, I'm hungry, can continue forever. These can be measured in decades for both soils and above ground. Reversibility of impact, irreversible in emissions reductions. Basically it's just capturing and putting back, so it's not really reversible in that sense once you do biosequestration. Biosequestration in soils can be reversed through return to poor farming practices or climate disasters, natural or anthropogenic. Above ground biomass can be reversed through return to poor farming practices or climate disasters. Ease of measurements is relatively simple, but very challenging to predict and measure here, and relatively simple when it's above ground. And this difficulty explains these massive differences in the estimates that we looked at before. Potential annual impact in terms of gigaton CO2 equivalent per year. It's strange to say annual and per year, but nonetheless 1.3 to 4.2 in terms of emissions reductions, 1.0 to 7.1 large range in terms of biosequestration in soils and above ground biomass, 1.1 to 6.4 gigaton CO2 equivalent per year. Here is a blurb. There is no single answer to addressing climate change. No silver bullets exist, but a silver buckshot exists. Okay, if we look at the whole landscape of climate solutions, we can see numerous opportunities to work together across economic sectors, geographic locations, and local to national scales, also international scales, honestly, to reduce emissions, create carbon sinks, restore healthy ecosystems, create jobs and local economic benefits while improving human well-being and stopping global warming. It can be done. The only question is, will we do it? Let's do it. Okay, so that's the entire report, and we will conclude here. I'll tend to put these podcasts in a couple of places. One under new findings in climate change, even though these are not exactly new findings. I'm always behind because I keep collecting literature, wanting to record, but billion other things happen, and I do this as I get time. Plus I also put these under other specific courses like drawdown or Earth system for mitigation and adaptation, and so on and so forth. Okay, see you in the next topic, which will be, what will it be? Maybe I can say right now. It will be maybe drought in numbers, drought photosynthesis, and droughts coming faster. So we'll go and look at few droughts. Okay, see you in the next podcast.